Astronomers have discovered nearly 6,000 planets orbiting other suns. From ultra-hot Jupiters where it rains molten iron, to frozen cinders under the ghostly flickering of a distant pulsar. From planets with 2 suns, to planets barely tied to a sun at all. And yet, out of all these planets, the one thing we haven't found is the one thing we expected to find. A planet like ours. A planet the size of Earth, in the habitable zone of a sun-like star. Nothing we've found out there in the universe looks like our home, with the only ones that come close being planets that orbit small red stars which have problems of their own, like giant solar flares. Part of our problem is that our telescopes aren't good enough to see our kind of solar system just yet. Our planets are not too small to see if we get lucky. Kepler 37b is smaller than Mercury. And our planets are not too far from the Sun to see if we get lucky. Tau Ceti F has an orbit a lot like Mars, and we know lots of Jupiter analogs. But to get lucky twice is too much to ask of our current techniques. That should change in the coming years with new data from spacecraft like Gaia, Plato, the Roman Space Telescope, and ultimately the Habitable Worlds Observatory. But for now, we have to wait. But that's just our kind of solar system. And there are many very different solar systems out there, just like there are many different kinds of planets. Some of them are super compact, some really spread out, and almost anything in between. And that was my inspiration both for this video and for my latest professional paper. I wanted to know if we could classify solar systems the same way we do stars and planets and galaxies. If perhaps we could even organize all the chaos we see in the catalog of exoplanets into a single diagram as simple and elegant as Hubble's tuning fork. And so I, along with my colleagues Juliet Becker, Chris Stark, and Fred Adams, set out to do just that. And yes, we did fit everything into one chart. We posted the preprint of the paper last week for the American Astronomical Society conference, and we expect to be publishing in the Astronomical Journal in a few weeks. I've linked it in the description so you can read it for yourself. But I also wanted to give a more visual overview of what we found for the lay audience. And so, in this video, I'll be showing you examples of each type of solar system in Celestia and explain what makes them unique. The first thing you'll notice about this chart is that we classify individual planets by their size. The exact details are technical and depend on who you ask. But the thing to remember is that Jupiters are about Jupiter-sized, Neptunes are about Neptune-sized, Earths are about Earth-sized, and sub-Neptunes are in between Earth and Neptune. And the most important thing to watch out for are Jupiters, because the gravity of giant planets has a big effect on their solar systems. Now let's look back at our solar system. Looking at the orbits to scale like this only tells you so much because the planets are too small to see. But with some clever editing of the Celestia source files, I can change the scale of the objects on the screen. Here, I've made the Sun 30 times bigger, and the planets 1,000 times bigger. Very much not to scale. In fact, Jupiter is bigger than the Sun in this picture. But you can see the planets now quite clearly. I'm also going to draw in the habitable zone, where liquid water can exist. This video isn't about habitable planets, but there aren't many points of reference in space, especially when you're changing the sizes of things, and this is a good one for comparison. It does change from star to star, but this will give you a much better idea of how big a solar system is from one to the next. Now, most planets we've discovered orbit pretty close to their stars, so I need to use a lower magnification, as it were, so they're not all on top of each other. For the rest of this video, I'm going to make the stars 5 times bigger than normal, and the planets 40 times, which is as big as I can go without having them touch each other. And I'll keep the scale factor in the corner of the screen just so there's no confusion. This is a useful scale because it means most stars and most gas giants will be drawn about the same size. So that's another point of reference you can use to tell the planets apart. It does still leave the planets looking like dots in our own solar system, but they'll be visible most of the time, and together with drawing in the habitable zone, I think you can get the picture. This is Kepler 11. It was the first big discovery by the Kepler Space Telescope in the year 2011. It's a star very much like our Sun, with a solar system very unlike our own. It has 6 planets, all of which are well inside the habitable zone, and 5 of which would fit inside the orbit of Mercury. And 5 of these planets are sub-Neptunes, a type of planet that we don't have at all in our solar system. Kepler 11 was a big deal when it was first discovered. We'd never imagined anything like it before. But in the years since, we've just kept discovering more and more solar systems that look a lot like it. In fact, out of the 300 or so solar systems we've discovered with at least 3 planets, 3/4 of them look roughly like Kepler 11, with planets bigger than Earth, all about the same size, and very close together. These solar systems were originally called compact Kepler systems, but in 2018, astronomer Lauren Weiss gave them a new name, Peas in a Pod. Weiss's team proved that planets in the same solar system being about the same size isn't a coincidence. They're too orderly for it to be random chance alone. And if you look at the ratios of orbital periods of each planet to the next, they're also about the same. All the planets in a given solar system look weirdly alike, hence peas in a pod, and the name stuck. Our own solar system doesn't look very much like Kepler 11. Our inner planets, Mercury, Venus, Earth, and Mars, are smaller. They're not all the same size, and they orbit farther from the Sun. But if you step back and look at the entire catalog, they're maybe not as weird as you think. It is true that our solar system is less regular than 80% of the peas in a pod systems out there, but that means it's still more regular than 20% of them. It's not completely out of left field, and we think the differences are more because it's just hard to see solar systems like our own. And once we can see smaller and longer period planets better, our solar system might turn out to be even less weird. Of course, our solar system also has outer planets, which Kepler 11 doesn't. But some peas in a pod systems do, and in fact, that may be the norm. This is HD 219134. It looks like a typical peas in a pod system with 5 planets, except if you look farther out, there's a 6th planet, very different from the others. A Jupiter-sized planet, or at least Saturn-sized. This system has both inner and outer planets. And just like our own solar system, there's a large gap between the smaller inner planets and the giant outer one, much like the asteroid belt between Mars and Jupiter. About 3% of the peas in a pod systems we've discovered have a distant outer Jupiter like this one, and that number is sure to go up when we look with the next generation of telescopes. In fact, based on formation models, we suspect it's very common. Now, you may wonder, could there be another planet, a Mars-sized planet perhaps, hiding in that gap? It's possible. We can't see all the planets after all, but it seems unlikely. For one thing, this gap is much wider than the Mars-Jupiter gap. You'd need 2 or 3 planets to fill it. And for another, there are both statistical reasons and reasons from theories of planet formation to think that even though we can't see all the planets, we probably can see all of the planets in the P-pod, so to speak. This gap and others like it are probably real. And so, the first part of our classification of solar systems, at least for systems with 3 or more planets where we can say something interesting, is to split them into inner and outer planets if we can. We haven't discovered that many outer planets yet, but where we do find them, they usually split pretty cleanly from the inner ones, just like this. Though that is with the caveat that the exact definition of what makes an outer planet is fuzzy around the edges. We came up with something that worked for the paper, but we really need to find more of them to get it right. Still, as it stands now, you'll rarely go wrong if you look for things that look like Jupiter in a Jupiter-like orbit. That seems to be the general pattern. We've discovered a lot more inner planets than outer planets, so we could do a lot more with classifying inner solar systems. Most of those are classic peas-in-a-pod systems, with all the planets looking mostly alike. But again, the most important thing to watch for are Jupiters with their massive gravity. Most outer planets are what we call cold Jupiters, far from their stars. But you can also have inner planets that are Jupiters, what we call warm Jupiters. And their solar systems behave pretty differently under the influence of their gravity, so we made them a separate category. The warm Jupiter systems have 1 or more giant planets as inner planets, and they are about 10% of the multi-planet systems we've discovered. We use the original peas-in-a-pod term broadly to refer to all solar systems where none of the inner planets are Jupiters, and they of course make up the other 90%. And there's one other rarer kind of solar system I should mention, the hot Jupiters. This is 51 Pegasi b, the very first exoplanet discovered around a sun-like star in 1995. And this is where the scale factor I set starts to look pretty ridiculous. Obviously the star and planet are not almost touching in real life, but it does illustrate how extreme these planets are. Hot Jupiters like this one are giant planets with orbital periods of less than 10 days, closer to their stars than we thought was even possible before then. These hot Jupiters count as warm Jupiters in our classification, but they're different from the others. They are much less likely to have other inner planets near them, probably because in migrating to those orbits from farther out, they knocked all the smaller planets out of the way. Some hot Jupiters do have distant cold Jupiters as outer planets, like WASP-8a here. But it's very rare for them to have other inner planets. Meanwhile, other warm Jupiters, with orbital periods between 10 and 100 days, are much more likely to have close neighbors. The first warm Jupiter system to be discovered with multiple planets was GJ876. Its 4 planets were discovered between 1998 and 2010. And it's a strange system compared with what we've seen so far. It has 2 Jupiter-sized planets in the middle of what we would call the inner planets, sitting in between a Neptune and a sub-Neptune. not at all like the simple peas in a pod systems that dominate the catalog. Although you might notice about GJ876 that it has a big gap in between the first and second planets. Does that mean anything? Would that actually make the two gas giants outer planets? But it seems like a silly way to define it when all 4 planets would still fit inside the orbit of Mercury. This is a different phenomenon that we saw specifically with inner planets. Some solar systems have large gaps among their inner planets, and not just between inner and outer. And this can apply both to warm Jupiter systems like GJ876, and some peas in a pod systems like Kepler-62. So we divided our 2 classes of solar systems again, with closely spaced inner systems, which have no conspicuous gaps between their inner planets, and gapped inner systems, which do. And it turns out that the gapped systems are also uncommon at about 10% of the total, although they are more common among warm Jupiter systems. This gives us 4 types of inner solar systems overall. Gapped peas in a pod systems like Kepler-62, gapped warm Jupiter systems like GJ876, closely spaced peas in a pod systems like Kepler-11, and closely spaced warm Jupiter systems like Rho Coronae Borealis. And you can count hot Jupiters as a 5th type. Despite their small numbers, though, the gapped systems also show variation among themselves, depending on where the gap is. For Kepler-62, it's in the middle, but that's fairly rare. More often, you see systems like GJ876, where the gap is between the first 2 planets. We think there are different formation and migration processes that can sometimes cause the innermost planet to separate from the others and drift closer to the star, so we gave them a separate category and called them inner gap systems. On the other hand, you can have systems like Kepler-150, which has 1 planet far outside the other 4. You could just call this an outer planet, but it's not quite the same. It's not that far out. In fact, it's in the habitable zone. And it doesn't look like an outer planet. It's only Neptune-sized and not Jupiter-sized. This is one of those places where the definitions get fuzzy, but we ended up calling it an inner planet, and creating a new category for things like it called outer gap systems. Not to be confused with the separate category of outer solar systems. That could change in the future, but it seems to work for what we have now. And of course, you also have rare middle gap systems like Kepler-62. There is still one problem with this classification. The same problem we had with the inner-outer divide. Could there be more planets hiding in these gaps? There could, yes, but there's good reason to think there usually aren't, because closer to the star, we'd be that much more likely to see them. And if they do manage to hide there without being seen, they're probably unusual in other ways. For example, for an exoplanet to hide in the gap between the 3rd and 4th planets of Kepler-62, it would have to be conspicuously smaller than the others, one of which is already Mars-sized, or, for transits, it would have to have an orbit that was conspicuously tilted relative to the others, both of which would make it stand out from other peas-in-a-pod planets. So even if there are other planets there, there's definitely something different about the gapped systems. That is how we classified inner planets in a nutshell. Outer planets, again, all look basically like Jupiter. mainly because it's much easier to spot large planets than small ones far from the star. One thing we did notice is that outer planets tend to be more spread out than inner planets in terms of ratios of orbital periods. This may be because of their larger gravitational influence. And there's one other complication to outer planets, which is that not all of them have corresponding inner planets. This is 47 Ursae Majoris. Its innermost planet was the first long-period exoplanet to be discovered in 1996. And it looks like an all-gas giant system with 3 outer planets and no inner planets. That doesn't mean there are no inner planets, though. In fact, there's a good chance there are. It just means that we can't see them. And unfortunately, that's pretty common because we search for them using different methods. Inner planets are usually found by transits, and outer planets by radial velocities, which often don't overlap very well. This is another area where we need to wait for the next generation of telescopes to learn more. Still, out of the roughly 300 solar systems where we have good enough data, we can classify 97% of them pretty well. That's something that probably would have surprised a lot of astronomers just a few years ago. It certainly surprised me. For the past 30 years, astronomers have been trying to wrangle an increasingly complicated zoo of exoplanets that has included one unexpected oddity after another. But, just like the puzzle of the particle zoo in the 1960s was solved by the discovery of quarks, the exoplanet zoo also seems to have clear organizing principles that let us classify it into different types of solar systems. But, as with all fields of science, there are still mysteries left to be solved. What's going on with the other 3% of systems that aren't so easy to classify? Some of them are just down to the fuzziness of where to draw the line between inner and outer planets. But there are a few solar systems that just don't follow the normal rules. This is HD 10180. It's a remarkably sun-like star. In fact, it's considered a solar twin. But its solar system is anything but normal. It has 6 planets, all of which are Neptune-sized or close to it. And rather than being split into inner and outer planets, they form a closely spaced system that straddles the ice line, the line where ice starts to form during planet formation, which is normally what draws the boundary between inner and outer planets. Some of these gaps are kind of big. In this case, we could tweak the definitions a bit and get distinct inner and outer planets out of it, but it doesn't look right. It doesn't look like an inner and outer system. In fact, it looks a lot more like a normal peas-in-a-pod system scaled up. You can compare it with Kepler-11 to scale, side by side, and they're pretty similar except in size. Both the size of the orbits and the size of the planets. HD 10180 is something that looks totally new, and it's not clear why. Things like it should be easier to detect, but so far this is the only one we know of. But it's not the only strange thing. If HD 10180 is scaled up, there's another solar system that looks an awful lot like a typical peas-in-a-pod system scaled down. TRAPPIST-1. TRAPPIST-1 is one of those famous solar systems that has some of the best candidates for potentially Earth-like planets, but it's also unusual because it has 7 small, Earth-sized planets squeezed in tight around a very small red dwarf star. Everything about this system is in miniature. Granted, if you compare it with other red dwarf systems, TRAPPIST-1 maybe isn't as weird as it first seems, but there's another solar system out there that's even more miniaturized. This is Kepler-42. It's another low-mass red dwarf, but its planets are even closer to it. 3 planets, all with periods of less than 2 days. No other known solar system has more than one planet that close in. These 4 systems seem to define the possible range of scales for peas in a pod, which is an interesting puzzle in itself. We don't really know why that would be. Another solar system that doesn't follow the normal rules is HIP 41378. By our definition, it's one of the rare middle gap systems, but you could also see it as having a strange inner and outer structure where instead of one Jupiter as an outer planet, it has 3 Neptunes surprisingly close together. This is another one of those cases where the definition of inner and outer planets is fuzzy, and we might want to rethink it in the future. And there's another strange thing about this system. The outermost planet, HIP 41378F, is also what is known as a superpuff, a planet with extremely low density, too low to be explained by formation models. This planet is the size of Saturn, but weighs less than Neptune, and it is by far the longest period superpuff out of the 20 or so we know of. Yet another mystery. And there are still more oddities out there. Kepler 51, the only solar system with 3 superpuffs, and they are also the 3 lowest density planets in the entire catalog, as light and fluffy as cotton candy. Kepler 90, the only confirmed 8-planet system besides our own, and another one with a strange gap structure that's worth keeping an eye on. WASP 148, the only solar system to have both a hot Jupiter and a warm Jupiter at the same time. And finally, HR 8799. And this one isn't an illustration. This is an actual time-lapse of photographs taken by the Keck telescope in Hawaii. HR 8799's planets are all several times more massive than Jupiter, and they're so far from their star that we can actually see them without them getting lost in the glare. The innermost planet is farther out than Saturn's orbit, and the outermost is more than twice as far as Neptune. And yet, all 4 orbits are pretty close to circular. We don't think planets form that far away from their stars, especially such big ones, so to get 4 of them out there on circular orbits is yet another surprise. This is only the first attempt at a complete classification of exoplanet solar systems. There are sure to be refinements made as more planets are discovered, and maybe someone else will come up with a completely different system that's even better. Honestly, I think half the value of our paper is in having a simple visual reference for all the solar systems that don't fit the peas in a pod model together. But this classification does cover everything that we know is out there now, and it shows us that the wild diversity of exoplanets is more understandable than we thought. So here's to the next 6,000 planets and beyond, in the hopes that we will learn even more about these extraordinary worlds.